People tend to struggle with algebra because they have a bad perspective of it. The most useful perspective on algebra is as a simple and flexible language for working with patterns. We're going to take this perspective in this video and hopefully simplify algebra for you. We're going to walk through some basic examples from things that you already know. We're going to build up to a more advanced example where we're going to show you the full power of algebra. So before you came to algebra, you had to memorize the multiplication table almost certainly. All the multiples of 1 through 12. So things like 9 times 3, 8 times 7, and so forth. Now there are a lot of things here to memorize, and you quickly learned that there were certain patterns that help make this easier. Probably the first one that you learned was 1 times. So 1 times a number is that number. So you didn't have to memorize 1 times 1 through 1 times 12, you just had to memorize that 1 times any number is that number. And that not only fixed all of those memorizations, 1 times 1 through 1 times 12, but it also helped you with things that you didn't have to memorize. So if you saw 1 times 20, you knew that was 20. So this pattern simplified your memorization for you. Now not all the numbers had these simple patterns, but one other number that was pretty simple was 10. So if you had 10 times a number, it was just that number with a 0 on the end. So this likewise saved you from having to memorize 10 times 1 through 10 times 12, and it also helped you to know 10 times numbers that were not numbers you needed to memorize. So 10 times 50 is 500, 50 with a 0 on the end. The question becomes, how far can you take these patterns? And this is what algebra is about. Algebra is about working with patterns and figuring out how to make them benefit us. So these two were very simple, but there were more advanced patterns that you could get into. So something another step up would be a pattern over top of these two. So let's look at 11 times 12. This is one that people often forget. I even forget it from time to time. If you do forget it, you could use a pattern to figure this out. You could say 11 times 12 just means 11 12s. So 11 is the same as 10 plus 1. So 11 12s is the same as having 10 12s and then another 12. So that means you have 10 times 12 plus 1 times 12. Now you'll notice here, I didn't have any kind of a pattern for 11 times 12, but I used this pattern to break up the 11, and now you'll see I have my two patterns from before. I know that 10 times a number is that number with a 0 on the end, so 10 times 12 is just a 12 with a 0, 120. And then 1 times a number is that number, so 1 times 12 is 12. So this is going to equal 132. It's not quite as fast as if you had just memorized 11 times 12, but it's pretty close. So by using a pattern, and in this case it's really 3 patterns, we've figured out how to figure out 11 times 12 even if we forgot it. So patterns can get a little more complicated, and also you can start combining them. So the question becomes, how do we work with these to find out how far we can go? Well, this is where our algebra language will come in. So this trick of breaking up the 11 into a 10 and a 1, we can write this in our language of algebra as 11x equals 10x plus x. That's how you would typically see that in an algebra class. The reason for this is that it's trying to simplify things down in a clear and concise way. But when people look at this for the first time, they don't really think clear and concise. The way that I would think to write this for someone who hasn't really seen this before is more like this. So 11 times a fill in the blank equals 10 times a fill in the blank plus a fill in the blank. And these are actually both algebra. Algebra is flexible. Algebra allows you to write things in such a way that they're meaningful for you and help you see what you want to see. So when we have this fill in the blank, that just means that we would fill in our number. So if we had our 12, we would just put our 12 in here, just like we had before, but we could put in some other number besides 12. So this is something that I feel like benefits a lot of people who haven't seen the X before, but these are really both algebra. It's flexible. It's what's going to help you. Another way that might help you is you could say 11 times a question mark equals 10 times a question mark plus a question mark. Maybe that's more meaningful for you. Algebra builds in that flexibility. You can name things what you want so that you can easily see what's going on. Now, the reason people picked X hundreds of years ago was just because that was what was simplest and easiest for them at that time, even though it doesn't necessarily make as much sense for us. But again, take advantage of that flexibility. Algebra is here to help you. It's not here to complicate things for you. The other thing you'll notice is the 11 is directly next to the x. It's not 11 times x and 10 times x. And the reason for this is the multiplication is the default operator, so you just don't write it. And again, this is the simple part of algebra. It tries to boil things down to make things as easy to write and as simple as possible. So the other part about the simplicity of algebra is that it doesn't cover everything, and that's intentional. It only covers a few things, so you don't have to know absolutely everything, but you can build a lot of things from it. And in general, that's a typical life problem, is we don't have enough time and brain power to know absolutely everything, so we have to boil complex things down into a few basic building blocks that we can kind of maneuver with to get to where we want to go. So, for instance, when I say algebra doesn't cover everything, if you look at our 10 rule, 10 times 8 equals 80, for example, there's no way in algebra to directly mess with the digits of a number. There's no way to say add a 0 or add a digit to this number. And that's intentional. Algebra only covers a few very basic things that you can do. You can add things, you can subtract things, you can multiply, you can divide, you can do square roots. There's a few other things that you can do, but there's nothing in here that directly messes with the digits. When we get to our advanced example here in a moment, you're going to see that we can kind of get around this, and that's again where the power of algebra comes in, but it leaves certain things out and it tries to just use a few very basic building blocks that tend to be useful. So it's simple and it's flexible. It's meant to make things easy. The other thing that I'll point out before we get to our advanced example is that algebra doesn't have to exist in isolation. For instance, 7 times 7 is 49. This is something that I know from a personal memory. My uncle's favorite football team is the San Francisco 49ers, so that's how I know this one. And that's not a math thing, that's a personal memory thing, but I can apply algebra on top of that. So 7 times 8, I can use the same trick as I did with 11 times 12. I can say this is 7 times 7 plus 1 times 7. And now these two pieces are easy for me to know because I know this 7 times 7 from my personal memory. So this is 49, and 1 times 7 I know from the simple pattern is 7, so this is going to be 56. So algebra doesn't have to exist in isolation. You can solve your problems with completely algebra, you can solve it with no algebra, or you can solve it with a combination of algebra and other things. It's completely valid to mix and match. You're not stuck in a bubble. It's here to benefit you. So in order to see the real power of algebra, I'm going to walk through a more advanced example. If you don't get every single thing from this example, that's okay. The idea is just to see a few things that you might not have seen before and see how this can really be useful. So in algebra, it's kind of like chess. It's like a chess game. Sometimes a strategy may be a lot of moves, and the first few moves may not really make a lot of sense, but they come back to a final conclusion that you're looking for. So we're going to start with some moves that don't make sense, and they're going to come back to our memorization problem. And in general, this is a thing with algebra. You start somewhere that might not seem like it's related, and then you start messing with things and looking at things from a different way until you can get to where you want to go. And that's why this language, this flexible and simple language is so important, so that you can rewrite things in a way that's easy to see what the next step is. So if you want to find something unusual, typically you have to try something unusual. So we're going to try something unusual. We're going to take a number and we're going to subtract the sum of its digits. So 17 minus 1 plus 7. So that's 17 minus 8 is 9, is 9 times 1. Let's try this with another number, 56. 56 minus 5 plus 6, that's 56 minus 11, that's going to be 45. This is 9 times 5. So we're starting to see, and this isn't something that might be obvious to you at the outset, but if you really start messing around with things, you start to see that this is 9 times something. So if you take a number and you subtract the sum of its digits, you're getting multiples of 9. Now the question is this true? Well, you can't try every single number. There's too many. But algebra can help us here, because algebra gives us a way of writing things so that it's simple and flexible. So we can write this in a simple and flexible way so that we can see what we want to see, where otherwise it would have been difficult to see. So we covered before that there's no way to directly mess with the digits in algebra. That's something that's left out. But we're going to be able to actually mess with the digits a little bit in a different way using what we do have. So we're looking at a number, and I'm going to call it n. Again, the flexibility of algebra. I can name things in a way that benefit me, so I'm going to name my number n since it's the number, it's easy for me to understand. And I'm looking for minus the sum of its digits, so s for sum of its digits, s as in sum. So this way I can easily tell which one's which. This one's the number, that one's the sum, and it's easy for me to understand. So this is really what I'm doing. I'm taking a number and I'm subtracting the sum of its digits. Well, the sum of its digits, well, digits I can write out, right? I can say the sum of the digits are going to be, and I can start this way, d1 plus d2 plus d3 and so forth, where d stands for digit, and I know there's some number of them, so I just start numbering them from 1 just because that's the easiest thing for me to do. And then I don't want to have to write out who knows how many of these because I don't know how many there are, so I just put a dot dot dot, and the dot 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 just means that the pattern should be obvious by that point, just like it does in the English language. So this is easy for me to write. The s is easy for me to write. Now the n, I can break this up in terms of algebra that matches this. And the way that I do that is I would say the number is going to be the first digit plus 10 times the second digit plus 100 times the third digit and so forth. So here, even though I don't have a direct operation to mess with the digits, I can use addition and multiplication to fake it. And it just so happens to match the sum of my digits. So here I can get away with the fact that algebra doesn't cover everything. I can rewrite this just using the addition and multiplication to match the form of this. So n minus s, so I can replace n with this, and I can replace s with this. So this is going to be d1 plus 10d2 plus 100 d3 minus d1 plus d2 plus d3. And now we see that things kind of match up a little bit, so this benefits us. So now we can combine things and see if we can make it simpler. The other thing I want to point out is I put in these parentheses. So parentheses means that everything inside of them belongs to the same group. So anything outside the parenthesis applies to every item inside of the parenthesis. So before I had s and n, but now I'm saying, well, n is composed of these pieces. It's kind of like a pizza. If you have a pizza, you can either look at it as an entire pizza or 6 or 8 slices or however many slices it's cut into. So here I'm saying n consists of these slices and s consists of these slices. So if I'm applying something to the whole, then I have to apply it to each individual slice. So that's why I put these parentheses. So that way I know that whatever applied to the entire thing now applies to all the pieces that make up that entire thing. So this minus applies to each item inside here. And this comes more in handy later. It also helps you later in this problem. It also helps you to see things more easily too sometimes, which we're going to see a little later. So here, let's work this out to try to simplify this down. So let's see if we can match things. So d1 minus d1, those are going to cancel, give me 0. 10d2 minus a d2, 10 minus 1, 9d2. 100d3 minus a d3, that's 100 minus 1 is 99d3. And this pattern is going to continue. Next one's going to be 999d4, and so forth. And if the pattern wasn't obvious to you, you're always free to take more terms until it is. You don't really want to write this ... until it actually is obvious, because that's what it means. So our overall goal is we wanted to say n minus s, a number minus the sum of its digits, is some multiple of 9. So wouldn't it be nice if we could write this as some sort of multiple of 9? And the way that we would say that with our grouping thing is there would be a 9 and then something in a group. And so that's a question that you might ask yourself a lot when you're working with algebra patterns. Wouldn't it be nice if try to reword things, try to finagle things so that they fit in just the right way so that you can see things in the way that you want to see them. The way I really want to see this is I want to see this as 9 times something. So is that true? Well, 9 times 1 is 9, so this is just going to be d2. 9 times 11 is 99, so this is 11d3. 9 times 111 is 999, so 111d4, and so forth. So now I have what I'm looking for. My number minus the sum of its digits is 9 times something. So that means any number minus the sum of its digits is a multiple of 9. So algebra has showed us what we couldn't do without it before. It showed us that any number minus the sum of its digits is a multiple of 9. So this is why simple and flexible language helps us. It's because it allows us to see things in just the right way so that we can easily understand how things are working and get to a result that we really want. So even though this got us to the result that we want, it hasn't exactly helped us with our original problem of helping us with the memorization and the multiplication table. Well, if I put this down, our newfound fact, a number minus the sum of its digits is 9 times something. And so this something, I don't care to know what it is, so I just come up with some random name, and the first random name that you typically use in algebra is x, so I just say x. So that's what this statement is. And any number minus the sum of its digits is 9 times something. So how does this help us? Well, again, in algebra is about making things easy for us. So we want to try to maneuver things so that we can see something that would help us. So let's take another couple of steps. How can we look at this in a different way so that it might be helpful to us? Well, one thing that you do a lot in algebra is you move things between the different sides of the equal sign. And so the way that you do that is by looking at it in a different way. So let's say I have 15 minus 10 equals 5. So that's one way of looking at these numbers, but these numbers are related in different ways. So to say that 15 minus 10 is 5 is like saying that 15 is 5 bigger than 10, or that 10 is 5 too small. So the 15 is 5 too big for 10, or the 10 is 5 too small for 15. So we could say, equivalently, that the 15 needs to come down by 5 to get to 10, or the 10 needs to come up by 5 to get to the 15. These are the same things, it's just worded in a different way. And that's, again, a lot of what algebra is about, is that flexibility. You want to twist things so they become obvious for you. So let's take that into account up here. N is the bigger number, S is the smaller number, so N has to come down by 9x to get to S, or S has to come up by 9x to get to N. So do any of these help us? Well, this N we know is our number, and we're predominantly interested in numbers, not in sums of digits. And well, wouldn't it be nice, and again, this is trying to see a few steps ahead, which you get more used to the more that you play with algebra, but wouldn't it be nice if maybe this was a multiple of 9? Because that would mean something. If this whole thing was a multiple of 9, that would mean the sum of the digits is a multiple of 9. And maybe that gets us somewhere. Well, how would that happen? Well, if our number is a multiple of 9, let's say n equals 9 times something, and so again, I don't care what that something is, so I come up with a random name, but I already used x up here, and this might not be the same something, so I just name it something different that's just, some random letter. And typically in algebra they use the letter y after x is used. So let's say n, my number, is some multiple of 9. Well, if I put that in here, that's going to mean 9y minus 9x equals the sum of the digits. And I can use my grouping trick to make this more obvious, if it's not already. And I can say, this is 9 times something. So again, we're using the flexibility and the simplicity of algebra to twist things in a way that helps us and benefits us. Not letting algebra twist us in a way that makes us confused and lost. So this means that the sum of the digits is a multiple of 9. So if I have a number, it's a multiple of 9, the sum of its digits must also be a multiple of 9. So that's somewhat interesting. So let's go to our multiples of 9. So when we had to memorize things, we had 1 times 9 through 12 times 9. So 1 times 9 was 9, and that's a multiple of 9, right? The sum of the digits of 9 is 9. It's 1 times 9. 2 times 9 was 18. 1 plus 8 is 9. That's 9 times 1. 3 times 9 is 27. 2 plus 7 is 9. That's a multiple of 1. So we're seeing if we have a 2-digit number, the only way that we can really get to a multiple of 9 is if we have these numbers equal up to 9 or equal up to 18, right? Because if we come down here, 11 times 9 is going to be 99. The sum of these two is going to be, these two digits is going to be 18, which is 2 times 9. So this is the max sum that you're going to get out of a 2-digit number. So if 9 times something is a 2-digit number, it's either going to add up to 18 or it's going to add up to 9. And the only one that can add up to 18 is this one, because you have to have 2 9s to get to 18. So everybody below 11, we know that the sum of those 2 digits are going to be 9. So that gives us a little bit of a rule. And the other thing that we can see here, so these 2 digits have to equal 9. The other thing that we'll see here is that this first digit here is going to be 1 minus whatever we were multiplying. So 2 minus 1 is 1, 3 minus 1 is 2, and then the second digit is whatever we need to add to get to 9. So we have sort of this little rule that we just figured out for these multiples of 9 that you might not have seen before. So 1 times 9, and well, really 2 times 9, because 1 times 9 we already have such a simple rule for that we just want to ignore that. And also this is a 1-digit number, so it's not as useful. But 2 times 9, really through 10 times 9, which is going to be 90. And we have a rule for 10 times 9, so maybe you could say 9 times 9. So we're going to go from here to here, 2 times 9 through 9 times 9. All you're going to do is you're going to subtract 1 to get this first digit, and then you're going to add whatever needs to be added in order to get to 9. And you've got a pattern. So you may realize that now we've used something that seemed completely unrelated, and through a bunch of steps, admittedly a lot of steps, we've gotten to something that's interesting and helpful for us for our memorization problem. And in fact, you can even take this farther, because this works, again, like any pattern, like our 1 times pattern. It works for things that we didn't have to memorize. If you have a gigantic number, 9 times 11,324, well, now you have an ability to check that, because if you get that number and you add up all the digits and it's not a multiple of 9, then you know that something's wrong. So you have a new tool that you can use that you might not have been able to figure out before without algebra. This is something that would be really complicated to figure out without algebra, and that's what algebra is here for. It's here to make things simple, and it's flexible for you so that you can see things in the way that you need to see them so that they're easy for you. And it's okay if you don't understand everything. No one knows everything about everything anyway. You just need to get the points that really benefit you, the main points that help you the most, and just use those to best effect, and try not to get lost in all of the details. Just try to focus on what really matters. This is meant to be simple and flexible. It's meant to benefit you, and just try to leave it at that, and not let this get complicated and make you miserable.